Hello everyone, welcome back to my channel AI Shorts. So in this particular video we're gonna see implementation of the multi-head attention using PyTorch from the scratch. So here I'm already assuming that you would be already familiar with the attention. If you are not familiar with the attention, please check out my other videos. So in this particular video I'm going to importing a bunch of libraries. I'm using a PyTorch for this demonstration. So I have few variables here. The sequence length, it is nothing but the length of the input sequence which we give as an input. So here my input sequence length is 4, which is nothing but that I have length of the 4 input sequence with the 4 words. So it's a maximum sequence length, so that all the vectors would be of fixed size, and we have set the back size to 1 for the demonstration purposes, and we then have a input dimension. So input dimension is nothing but which is a vector dimension of every word, so that goes into the attention unit. And d underscore model, this is the output of the attention unit for every single word. So these are the dimensions I am considering initially. So I am creating a using Torch, I am creating a random normal distribution of this particular input, where batch size is equal to 1 and sequence length is 4. And input dimensions is 512, which represents the input dimension of the input. So you can see here I am executing this cell. The size of this cell is 1 cross 4 cross 512. So now I am creating a linear layer. So now this X over here, you can see it's randomly sampled input. Since I am not going to creating the positional encoding in this input phase right now, so I am just generating some random data. So the input is going to be a batch size of batch size cross sequence length cross input dimensions, so which is 1 cross 4 cross 4. Note that this X value is not the value over here, but it's the value that is input after the position embedding addition. Now we are going to be mapping the input from dimension of 1 times the model dimension, which is the 3 times. This is done to create the query vector, the key vector, and the value vector of all concatenated, and all of them have 8 attention heads, which we will split it up later. We then pass the input to this layer to generate the QKV vector, you can see, and this is its dimension. So it's one batch, 4 words, and so I am passing here the X to the QKV layer. So output shape of the QKV is 1 cross 4 cross 1536. Now I wanted to get an idea what kind of values we see here. Since I am sampling from the random normal distribution, you will see the values like this. So but the distribution of all the values in this entire tensor is going to be very difficult, depending on how we generate the data, depending on the positional encodings and the inputs. So we have 8 attention heads that we are considering here. So if you see here, we have 8 attention heads we are considering, and each is going to be 512 divided by 8, which is going to be 64. And now we will reshape our QKV matrix to break down the last dimension into product of the number of heads and the 3 times the head dimension. So here this 3 exists because it's a combination of the query vector, key vector, and the value vector. So we get a tensor back. It looks so here. If you see, I'm going to be perform the permutation around just the second and third dimension. So the head is over here, and the number of sequences will be over here. So it's easier to perform the parallel operations on the last 2 dimensions. So that it's easier to perform the parallel operations on here last 2 dimensions. Now we obtain the query key value vectors individually by basically breaking down this entire tensor by this last dimension. So here we use chunk for it to split up this particular query key and value. So if you observe here, that size of the QKV is 1 cross 4 cross 8 cross 192. Where 1 is nothing but the batch size, and 4 is nothing but the sequence length, and 8 is nothing but the number of heads, and 192 is the dimensions. So this is particularly the dimensions for the each head. So what we want to do is what we do initially is this is 0 1 2 3. So we'll keep the 0 as it is, and we will swap 8 to the 4th part, so that the sequence length which we have actually for the each head. So if you see here, the 8 is nothing but the number of heads, so we will swap the 8 to here, so we will be having the sequence length, which is the number of words, and the number of this is 192 is nothing but like it's dimensionality of the model divided by the number of heads. So D model is what we will provide as the input here. If you see, so we have provided the D model as factorial, which is the dimensionality. So if we made it into the chunk size of 3, making this last dimension. So this will be chunked into query, key and value. If you see, so this 64 belongs to the query, and this 64 belongs to key, and this 64 belongs to value. So 64 plus 64 plus 64, which is nothing but 192. So which we are getting here, output from the attention unit divided by the number of heads. So we made it into the chunks. Now we are actually going to perform the attention mechanism. So first of all, we are going to set the size of one of these vectors, which is nothing but the dk. So every word has the query vector, and it's going to compare its query vector to the all to every word's key vector. That's represented by the matrix multiplication over here, and we can represent that by this code also. So notice that you have to use this transpose function. You can't just perform the transpose, because these are the tensors that are 4-dimensional actually, and not simply represented by the 2-dimensional matrices. So we specifically transpose this along with the dimensions which we want to transpose, and we want to transpose sequence length and head dimension size, which are over here. So we are performing this transpose operation. Now if you see here, we are scaling in here in order to make sure that the variance of these values is much smaller, so that these values just don't go out of the control, especially since this is a trainable machine learning model, and here is the dummy example, just to show like how important the transpose is. Here is just a dummy example just to show how important transpose is, and also that it takes in these two values of which dimensions along which you want to transpose your tensors, and it doesn't matter like about the ordering, as long as the same dimensions are present, it will yield if you see the same result here. So like the transpose, we are comparing between these two values. So once we completed this operation, now let's talk about the masking. We notice here in that encoder we don't really require any kind of masking, whereas in the decoder we require masking for self-attention. This is done to ensure that the decoder does not cheat, and the goal of the attention mechanism is to gain context from these words that are around it. So during the encoding phase, we have all words passed in simultaneously, and in decoders we generate words one at a time. So when generating a context, we only want to look at words that come before it, because we don't even have the words that come after it. So we are basically going to have our scale tensor. So we are generating the mask matrix here. So in this particular mask matrix, like this is the tensor of one head, where the 4x4 matrix which we are having. So it's going to be looking like this, where we have the lower diagonal elements the same as what we scale. So would have been because we are just adding the zeros. So the upper diagonal elements, whatever the negative infinity is, we are doing negative infinity especially because we are going to be using a softmax operation, so which are exponents. The exponents of 0 will become 1, so the exponents of negative infinity will become 0, so that you cannot cheat and look forward. So if you see here, we are performing the operation between the scaled and mask operation between the scaled and mask input. So if you see here, we are performing the operation between the scaled and mask, and you see like the upper triangular matrix, these values are occupied with the negative infinity, and we are performing the scaled plus is equal to mask, which we perform generally in decoder. So once we perform this operation, if you see here, the exponential of 0.5596 and 0.5596 plus 0.44 plus 0.0404, which for this particular row which we are seeing. So we are also performing the softmax operation on this scale one. So here the you can match this 0.62 is exactly what we have got in this particular row for these two inputs which we are considering. So this is the basically the attention output. Now we take this values vector, so which is actually being offered, we now take this value vector which is actually being offered by every single word to generate the new value vectors. So the idea here is that these new value vectors are going to be much context aware than the original value vectors in the original input vectors. So we'll end up with, for every batch, for every head, for every word in the sequence, we'll have a dimensional vector. So I have created function that exactly everything that I just described. So I also added an optional mask function here, if you see, depending whether we are dealing with the encoder or the decoder. For example, if I just execute this, you will see that we have an attention vector. So taking this particular function, I initially pass mask as none. So if you see here, I am passing the initially mask as none. So you can see the attention output, which will be like this. But if I change this mask to the original mask, so you can see all these upper values have become zeros. So this is how we handle in the decoder to not see the the next word, which will be the masked. So the only first so the first word will not be able to capture the relationship with the next other words, and similarly the second word will not be will be knowing only the relationship with the previous word, and does not know relationship. It will not see the next few words, and if you see the third word, it will capture the relationship with the prior words only, and it will ignore the last one. So this is how we handle the mask retention by like feeding the negative infinity values. So for these initial values we will be adding the 0, but for these values we will be adding the negative infinity, so that once we take the softmax value, so what happens in the softmax is exactly what happens in the softmax exactly is like we have made these values as a negative infinite, so that will be converted as a 0. So this is fed as a query, and key value will be taken from the encoder, passing to the further attention. So this is how the masked attention will be handled. Now we have all of these value vectors for every single attention head and for every single word, which are dimensional vectors. So what we do now is we are going to now combine and concatenate all of those heads together. For the 8 heads which we are having, we are going to make now them dimensional vectors, which is exactly the input dimension. So these heads can communicate with each other, and the information they have learned, so we just pass it to the linear layer, which is a feed forward layer. All final code classes of this code entirely have combined together, as well as by creating this is the same function that I have also written class called multi-head attention. So it's going to be now taking a constructor, so which we will initial some of these parameters that I have talked about along the video, as well as see here we will be having the input, what is the input dimensions and what is the output dimensions, which we are gonna have, and what are the number of heads that we are considering, and what is the head dimensions. Head dimension is like output dimensions divided by the number of heads. Finally it concatenated to the d underscore model using a linear layer, which you can see here, and QKV layer which splits the input dimension, and 3 cross d underscore model, which is the output dimension from the attention layer. So we are having a forward layer. So what exactly happens in the forward layer is like we will be taking the input size, so which is the batch size we will be having, and sequence length, and what is the input dimension, and we have a QKV layer which we have implemented above. So in this QKV layer we will pass the initial input, and so once we pass this initial input, then we will be performing the reshaping based on the batch size and the sequence length, and the number of heads, and 3 into head dimensions, which depends on for all the query key and value. So once we perform this operation, we will be performing the permutation operation. So that we are performing the permutation operation, post which we will be dividing the query key and value into the 3 different chunks. So then we will calculate the scale dot product across this query key and value, and mask here is optional. So once we get the values, we will be reshaping the values by like by concatenating the number of heads and dimension of the each head, and finally we will be passing those values to the linear layer. Actually, in the original implementation, it also involves the normalization layers, which we are not considering as of now. So if you see here, I am passing the random input, like input dimension is 1024 and output is 512. So the number of heads, if you see here, is 8, and batch size is 30, and the sequence length is 5. So initially our input size is 30 cross 5 cross 1024, where the 1024 is the dimensional input for each of the word that is present in this input. So for example, I have sentence like this picture is looking great. So here we have the 5 words. So for each word we will be having a 1024 vector after the positional embedding addition for that particular input. And so this 1536 will be split across the 8 heads, where each head will be having the like dimensions of 192. And once after this we'll be performing the permutation operation over these dimensions. Then we will be having the queries, we'll be having the query and key and value vectors after the chunk, where we will be dividing these 192 dimensions into the query key and value using the dot chunk. And later we perform the scaled dot product between this query and key vectors. So once we perform this operation, we will be having the shape of the 30 cross 8 cross 5 cross 64, and which post which 64 will be merged and made into a single vector of 512, and that will be passed to the linear layer, where we'll be finally getting the 512 dimensions. So yeah, this is how like we'll be performing the attention. I hope like everything here made a lot of sense now. So for more intuition of transformer logic, please check out my other videos. And yeah, thank you so much for watching my video. If you like, please subscribe.